When waves come together like this, they add when they reach the same space. It's called constructive interference. When waves are, as shown below, when they come together, they will cancel each other out. That's called destructive interference. So that needs to be remembered. So when we have waves of the same wavelength coming to two slits like this, what happens is when they pass through those slits, they are diffracted as shown. There's the crest of the wave. And they keep propagating out, but notice right here at this spot is where the crests overlap and you have constructive interference. There's another spot and another spot and yet another spot. And they will keep giving this constructive interference. But that's not the only place where it happens. Look at this wave carefully. There's one there, there, there. And in fact, if I were to draw a screen at the top and pretend this was light waves, you would actually have constructive interference at all these places shown by the arrows, and you would have what's called a fringe of light. You have the bright spot and then a dark spot. Bright, dark, bright, dark, bright. And etc. It keeps going. They're called fringes. And you have to have light of the same wavelength, monochromatic light they call it. There's the light going through the two slits, and there is the interference pattern. Now we want to derive a formula that will tell us where the fringes are. So here's another way of looking at this. Here's a ray of light coming in, and it is diffracted as shown. Another ray is diffracted, and there will be a ray diffracted such that, look, all of the crests of those waves will do constructive interference as shown there. And follow this carefully. In order for them to have constructive interference, the one that has bent like this on the bottom has to have one wavelength or two wavelengths or three wavelengths so that the wave is perfectly in sync with the top wave. It's in phase with it, we say. So let me label this, and that will be n lambda. So let me simplify this diagram. I'm going to draw a red line there, and the dotted line is shown. That yellow line represents the first diffracted ray. Here is the second diffracted ray. I will call the distance between the slits d. The length from the slit to the screen is L, and it's huge compared to d, 10 to the 5th times greater sometimes. And we will call the distance from the dotted line up to where the first fringe happens y, or to the second fringe would be y. We'll call that y. There's n lambda and a little right triangle there. There's theta, and here also theta will be in the little green triangle. So look at this diagram, copy it out carefully. That dotted line is called the central maximum, and all the fringes are measured from the central maximum, and they would call that actually n equals 0. Now I want to derive the formula now, and y over L equals tan of theta, opposite over hypotenuse. But notice something. For small angles, the tan of theta equals sine theta. Now if you have trouble believing that, take your calculator out and try tan 0.5 degrees, then sine 0.5 degrees, and you'll see that for really tiny angles they're the same. And theta, in fact, here will be very, very tiny. So what I can actually say is the sine of theta is y divided by L. Now what that means is there's theta right there, that little check mark I put in purple, and I can say n lambda over d, opposite over hypotenuse, is equal to the sine of theta. And therefore, I can say n lambda is equal to d sine theta, and that's one of the very important formulas. We'll look at that in a moment. But now I can also say n times lambda is equal to d times sine theta is the same as y over L because the angle is small. And now I can rearrange that formula for y, and I will have an equation that will tell me where the fringes are to be found relative to that central maximum. Very important equation. NL times lambda divided by d. That's what y is. Now let's look at this a little bit more carefully, and I'll just identify and clarify what each variable means. Now they usually write the formula with an m instead of an n. And m represents an integer, 1, 2, 3, 4, 5. For example, the first order fringe, where the first bright light is the first order. The second fringe would be the second order, where m would be 2, etc. If you wanted the dark spot, you go up by halves. Lambda is the wavelength. D is the distance between slits. And obviously theta, sine theta, is the sine of that angle from the center of D to the screen is shown. But more important now, y is the distance from the central maximum to whichever fringe we want. It's the distance. And remember to keep the units the same, by the way. And that will help you to find y, and you need to memorize this formula. M, as we've talked about, is an integer, 1, 2, 3, 4, 5, that tells you which order you want, which one of the fringes you want. Lambda is the wavelength. L is the distance from the slits to the screen. And D is the distance between the slits. You really need to know how this formula works.
Double slits are cool because they show definitively that light can have wave-like interference patterns. And if you shine a green laser through here, what you'd see on the screen would be something like this. You'd have these bright spots, but they'd kind of blend into dark spots, which blend into bright spots, which is why when we draw a graphical representation of this, it kind of looks like this, where these spots are blending into each other, which is cool, but it also kind of sucks, because if you were to go actually try to do this experiment, you'd want to measure some angles. And that means you have to measure some distances. I'd measure distance from the screen to the wall. That would give me this side of the triangle. And then I'd also probably want to measure distance between two of these bright spots, because that's what I can see. But because they're smudgy, it's like, is that the center? Is this the center? Sometimes the light's not so strong and it's hard to tell. And what's worse is these kind of die off. And so there's another problem. These die off pretty quick. Sometimes you're lucky to even see the 5th or 6th bright spot down the line. So my question is there a better way? Is there a way to make these spots more defined and so you can see more of them so they're brighter? And the answer is definitively yes, and we figured out how to do it. And the way you do it is you just make more holes. So you come over to here, and if these are spaced to distance d, I'm just going to make another hole a distance d. And then I'm going to make another hole a distance d. And then I'm going to make another hole a distance d. I'm going to make hundreds, thousands of these holes extremely close together. As long as they're all a distance d apart, something magical happens. So if these are all d apart, what happens is, on the wall over here, instead of getting this smudgy pattern, you really will just get a dot right at there, and then darkness, and then another dot, and then darkness, and another dot, and you'll see this continue out much further than you could previously. Why? Well, let's talk about why. So let's talk about this. How come you see this pattern over here like this? So the first wave from this first hole, let's imagine this first wave from this first hole, it's going to travel a certain distance to the wall. Let's say we look at a point over here where it is constructive. So let's say we just had these 2 holes to start off with, right? 2 holes, double slit, disregard all this stuff for a minute. 2 waves coming in from 2 holes, get over to here. Let's say this is a bright spot. Let's say it's the bright spot that corresponds to delta x equals 1 wavelength. In other words, this would be the constructive point where the second wave from the second hole travels 1 wavelength further than the wave from the first hole. And again, what that means is if I were to carefully draw a line from here at a right angle right there, that means that this wave from the second hole, this is the extra part. So that would be 1 extra wavelength. And because this second wave is traveling 1 extra wavelength, it's going to be constructive because if I draw my wave, they're going to match up perfectly there. So if I draw my wave, let's say the wave from the first hole happened to be at this particular point on its cycle. It doesn't have to be, but let's just say it was there. The first wave hit that point at this point in its cycle. Well, the second wave, since it's traveling one wavelength further, is going to hit at this point in its cycle. So it'd be here. Now these are both hitting there at the same point. So the first wave gets there, hitting right here. The second wave gets there, hitting right here. These overlap because these are two different waves overlapping at this point. It's going to be constructive because if a peak matches a peak, constructive. If a valley matches a valley, constructive. How about the third hole? Here's where it gets interesting. This third hole, the wave from the third hole is going to have to travel this far to get there. Well, let's see. From the second, how much further does it travel compared to the second hole? I'm going to do the same game I did just a minute ago. It travels this much further, which, again, since these are the same angle, this is going to be the same distance here. This is also going to be one wavelength. Remember we derived this, that d sine theta is the path length difference. And the theta is the same for all of them. And so I could just look at these two, consider these two as a double slit. This one travels one wavelength further than the second. How much further does it travel than the first? Well, I'm going to continue that line down. It's just going to travel 2 wavelengths farther than the first. So the wave coming out of the third hole travels 2 wavelengths farther than the first hole. The second and the third are going to be constructive because they're 1 wavelength apart. And the third and the first are going to be constructive because they're 2 wavelengths apart. That's okay. 2 wavelengths, it doesn't matter. Look at, if the first one hits here, the wave from the second hole hits here. The wave from the third hole travels 2 extra wavelengths. When that third wave gets to this point, it'll be at this point on its cycle. They're all going to be overlapping at the same point on their cycle. It's going to be constructive. You can keep doing this. You can come down to this hole, and it'll also be constructive interference. In other words, this fourth hole travels 1 wavelength further than the third, 2 wavelengths further than the second hole, 3 wavelengths further than the first hole, but they're still all going to overlap perfectly. You will get an extremely bright spot here because now you have even more light overlapping, and it's all perfectly constructive. Bright spot. Now, here's where it gets strange. So you got to be careful. This is the part of the explanation I hated as a student. I thought this made no sense whatsoever, so pay close attention at this point. Here's the weird thing. If you deviate slightly from this constructive point, if I go up just a little bit over here to some point right here, let's just see what happens. This wave from this first hole would travel that far to get there. Okay. And the wave from the second hole travels that far to get there. The path length difference isn't going to be 1 wavelength. Let's say the path length difference happens to be 1.1 wavelengths. So let's say the wave from the second hole happened to be traveling not 1 wavelength further anymore. It's not traveling 1 wavelength further. It's going to be traveling 1 and 0.1 wavelengths further. And so if the first wave happened to hit at this point, the second wave would be hitting at not exactly 1 wavelength, but 1.1. Now if I keep drawing them over here, I'm going to run out of room. So since they're all the same points on the cycle, this cycle is the same over and over. 1 wavelength, 0.1, I'm just going to draw that right here. So the second wave would hit right there. Those would overlap. You know, that's partially constructive. I mean, you're going to get just looking at these, you'd think you'd get a bright spot. But if you keep going, let's see what happens. Wave from the third hole also travels to get there. How much farther does it travel? Well, it travels 1.1 wavelengths further than the second hole, but it travels 1.1 plus 1.1 wavelengths further than the first hole, so it travels 2.2 wavelengths further than the first hole. So to make this clear, let me just be clear here. So if I do the same trick, right, I draw this down to a right angle. It's a little farther, so I have to draw the line a little further out. First wave travels 1 wavelength and 0.1 wavelengths further. How about this one here? Well, the wave from the third hole travels 1 wavelength 1.1 wavelengths further than the wave from the second hole, but it's going to travel 1.1 plus 1.1 wavelengths further than the first hole. So it's going to be 2.2. This wave from the third hole is going to travel 2.2 wavelengths further than the wave from the first hole. Where would that be? So 1, 2 wavelengths. 0.2 would be even further down the line here, not completely to the bottom, but further down the line. So it would be at this point over here. And you can keep doing this, and let's just see what happens. Let's just do a couple more. This wavelength has to travel this far. So now you could probably see the pattern. This wave through the fourth hole has to travel 1.1 wavelengths further than the wave from the third. It travels 2.2 wavelengths further than the wave from the second. It travels 3.3 wavelengths further than the wave from the first. So if I compare this wavelength, where this wave is on its cycle compared to the first, then I'm going to be 3.3 wavelengths. So if I go 1, 2, 3, and then 0.3, it'd be down here somewhere. I'd get one that's at 0.4, I'd get one that's at 0.5, I'd get one that's at 0.6, 1.7, 1.8, 1.9, one at, well, 0.10, which is back to a whole wavelength, then wavelength again, a whole wavelength difference. What is this going to be? If all these waves are overlapping like this, at this point that's only slightly deviated from this other point, what am I going to see there? Well, this, look, you could pair these off. This point and this point are going to interfere completely destructively. One's at a maximum, one's at a minimum, one's at the peak, one's at the trough, and so you get 0. And you can keep pairing these off. This one here and that one there completely annihilate each other, completely destructive. And you can keep doing this one here and this one there, completely destructive. You can keep finding points that completely destruct each other, and that means you're going to get no intensity at all, even slightly off from this magical point, this magical integer wavelength point. What that means is instead of getting a blur, instead of getting this smudgy pattern, you're going to get at the bright spots a dot. And then another dot at the bright spot. And in between these bright spots, you will get darkness, which is great. It's great because it's easier to measure. So that's one good thing. And it relies on this fact that if you've got multiple holes, hundreds, thousands of holes, if you go off even slightly, because this isn't going to always match up perfectly, you keep going down the line, one of these are going to interfere constructively with another, and you can keep pairing these off, and then the second would interfere destructively with a different one, and the third with a different one, and the fourth with a different one, and they're always going to match up so that you can destroy them all, and you get destructive points in between. That's why it's dark. Now, at first, I didn't like that argument. I had to go back over that, make sure that made sense to me. So if it doesn't make sense to you, go through. You got to hammer it out, try it out, draw it out. I've tried my best to explain it here, but I have to admit it's a difficult one to sort of comprehend. But that's the idea. And so this is great, actually. These multiple holes here are giving us points that are spaced out and clearly delineated. Now I can clearly see, okay, if I wanted to measure this distance, I don't have to guess. There's no guesswork. One dot's here, one dot's there. Bright, no smudginess. So that's one great thing about this. The other great thing is because I've got more holes, this brightness lasts longer. These bright spots will keep going further. I can see this travel further down the line than I would with this smudginess because I've got multiple holes interacting. I'll have more intense dots. It's brighter. So the dots are more delineated and they're typically brighter, more intense. And so we give this a special name because this is so useful. These multiple holes, instead of a double slit, these multiple holes are more useful. We call this a diffraction grading. So this is a diffraction grading, and it's more useful than a double slit in many ways because it gives you clearly delineated dots and it lets you see them more clearly. And how many holes are there in a diffraction grading? Well, typically these are rated in lines per centimeter. In other words, if you took a diffraction grading and asked how many holes are there, the lines are the holes, how many holes are there per centimeter. Well, the lines could be the blocked parts, and the holes could be the parts where there's no blocked part, but regardless, there'll be as many lines as there are holes. How many holes are there per centimeter? There's typically thousands of lines per centimeter in a diffraction grating. That's how small these are spaced together. You might worry though, oh, isn't the math going to be complicated here? We've got all these holes here. Turns out no. This is the best part. By far the best part. This relationship still holds. All that math we did, still fine. And because these all line up for the good points, the magic points, these points where they all overlap in such a way that they're one wavelength further, those line up perfectly so that no matter how many holes you go down the line, they're all perfectly constructively interfering. And so you get this equation. You get the same equation. It's the same equation we had before where d sine theta equals m lambda gives you the constructive points for a diffraction grading interference pattern on the wall.